Move to the last talk of the session, which is on correctness, witness validation by abstract interpretation. So this is work by Simmo, Saan, Schwarz, Julian, Erhard, Helmut, Seidl, Tilscher, and Vesal, Vojdani, and Simmo is going to give the talk.
Thank you for the introduction. So in the context of our work, witnesses are exchangeable proof artifacts for program analysis results. And as we saw, these can be for violations like counterexamples or for correctness. And our work focuses on correctness witnesses only. And one place they are used is SVComp for the computational software verification. And there are witness validators which are based on model checking, test execution, etc. But so far, the ones for correctness witnesses were all based on model checking. And the competition organizer, Dirk Baer, has in a recent report stated that there is a remarkable gap in software verification research because there are results that cannot be independently confirmed. Therefore, the goal of our work is to complement existing validators by developing a new abstract interpretation based correctness witness validator. So first, a couple of definitions. We assume there's some kind of program P, and the set N of its location and the set V of its variables. We also assume some kind of invariant language is being used, for example, C expressions, which are currently in SVComp, or ACSL, something else. And with these definitions at hand, we can say that the correctness witness for a safety property of a program is this tuple where the W component is a mapping from program locations to their invariants. And some or many of these might be these trivially true invariants as well. And the note is that these location-based witnesses, they are simpler than the automaton-based ones that have been used in SVComp for a long time. Now, such a witness, it is valid if the program satisfies the property, and whenever the execution reaches any particular location in it, the invariant at that location should hold. And the witness validator then is a tool which attempts to prove that the witness is valid, so it is checking both of these conditions. However, SVComp has used a slightly weaker notion of witness validation, which we call witness-guided verification, where actually only the first point is being checked. But in that process, the tool might look at the witness invariants as some kind of hints or guidance. So quickly about abstract interpretation, we assume some kind of abstract domain D with all the usual suspects, widening and narrowing. We assume some abstract semantics for the primitive statement like assignments, assumes, and havocs, which non-deterministically assign a set of variables. And then an abstract interpreter combines these things, probably does some fixed point iteration, and gives us a mapping sigma from the locations to their computed abstract values. And now we can think about witness validation again. So a witness is validated if this computed sigma is sufficient to show that the property holds for the program. And for every location, the invariant is true in all the concrete states corresponding to the computed abstract ones. But this requires a concretization, which is maybe not very practical. So a realistic tool might evaluate these invariants abstractly instead, which is less precise but still sound. However, as it is formulated here, witness validation is simply extra work for the abstract interpreter. It also has to check the second condition. But we would like somehow that we benefit from knowing the invariants ahead of time, which some other techniques already do. And for this, we study witness-guided verification in this first point, and we want to achieve three things simultaneously. So we want to use the invariants in the witness to somehow reach a fixed point, which is maybe more precise, or to reach it in fewer iterations. At the same time, we have to avoid overshooting the property that we want to prove about the program. And finally, we should not trust the invariants in the witness to be correct. And I will illustrate our technique with a small example. So first, here is there's no witness. We will just do a normal interval analysis on this tiny program on the left. At the end of the first loop iteration, we first get there with the interval from 39 to 39. At the beginning of the second iteration, this is joined with the initial value. It's a loop head. We apply widening, and we lose the lower bound on this variable. And then we can do another iteration. We reach a fixed point. We can try doing narrowing there, but this won't help in this case. And we have no lower bound for this x. But now suppose we have a witness which gives us this invariant that x is between 0 and 40 at the loop head. How can the abstract interpreter benefit from knowing this? Well, in our technique, when we reach this loop head, well, we first time reach it within this interval from 40 to 40, and what we want to do is to relax this abstract value according to this invariant expression that we were provided into a less precise one, in this case, the interval from 0 to 40, and then continue interpreting the program. And then we see that we reach a fixed point in a single iteration. And then we actually gain two benefits here. First, we managed to confirm a stronger invariant about this program that we could not infer from scratch, and we did so in fewer iterations of the abstract interpreter. And we might not always get both of these benefits. So to go more formal, we will now look at this relaxation step that we did there. And for this, when we are given a witness, we will insert into the program special unassumed statements with the invariants that were given by the witness. And the concrete semantics of these is that they are completely a no-op. The abstract one is, however, that we want to relax the states in a way which is somehow dual to the usual assume operation, which takes a less precise abstract state and, according to the expression, refines it into a more precise one. And our operation should go the other way, from this more precise thing with a different expression to the less precise one. And by choosing witness invariants suitably, we can give up this precision in a controlled manner and hopefully verify the program still. And now we will look at abstract operators corresponding to these unassumed statements. And we also have this sub v here indicating the set of variables we want to actually relax, which will somewhat simplify things. And what we want is that these operators be sound with respect to the no-op semantics. And if that is the case, then the entire abstract interpreter remains sound with respect to the original program as well. Now, because the concrete semantics is a no-op, we will specify the intended abstract behavior through a number of examples. So first, suppose we have an abstract state with many variables in it, but the invariant is only speaking about some of them. Then others should remain fixed in this operation. And this means that witness invariants are not required to describe complete program states at all program points, but they can only speak about the relevant variables at every point. The role of this set V is shown in the second example, where if the invariant has multiple variables in it, we might still want to keep some fixed and relax only the others. Now, things get a bit more interesting when we look at the relational abstractions, and there let's think about the state where that describes that 0 is equal to x and x is leg of y. And now we want to relax this first equality into an inequality. Here's the same thing spelled out with octagon constraints, but the key here is that when we are relaxing this x and this first equality, then we want to preserve the inequality between x and y here. And finally, we would like these unassume operators and the witness invariants to be able to leverage things that the abstract interpreter is already computing, for example, points to sets. And then this would allow us to provide witness invariants through the just pointers without having to explicitly state the points to sets also in the invariant. But this is particularly necessary for programs with dynamic memory allocation, where the only way to refer to these values is through the pointers. Now, one very naive way to define such an unassume operator is to just havoc the variables we want to relax and assume instead the expression that we want. And to remain sound, we also join it with the incoming abstract value. And this works very nicely for the simple illustrative example that I went through before. But where it fails is exactly this relational example, because when we are havocing x, we immediately lose all the relations between x and anything else. So how can we alleviate this? We will make use of a dual narrowing operator, which, given two abstract values d1 and d2, returns something between them. And this gives us a scale to tune the precision of such operator. And what we do is we take the previous unassume and we wrap it with this unassume operator, and by choosing suitable dual narrowings, we can make the unassume do what we want in a suitable level of precision. And this succeeds for the relational example we have in the paper. Defined a specific instance of a dual narrowing for relational domains, which makes it work, and it exploits abstract domains with heterogeneous environments. So you have abstractions which use different sets of variables potentially overlapping, and how to, for example, join them together. But where it still fails is with pointers, because this abstract assume operation, it cannot refine things through ambiguous point to sets, but we would like to do that. And therefore, we look at a classic algorithm, HC for revise or backwards evaluation. It is commonly used to implement the abstract assume operation for non-relational domains in a syntax-driven manner. And it works very intuitively. You have an abstract state where maybe x is from 40 to infinity, and you want to refine it with this equality. We can think about this equality in abstract terms. We want this equality to evaluate to a definitely true Boolean in our abstractions. Then we can use the backwards operator for equality here to compute from the value of the entire expression, the value of its right argument, what should the value of its left argument be. And similarly, using the backwards operator for plus, compute what should the value of its left argument be again? And then we get a more refined value for this variable in this expression and can construct a more refined state. And this algorithm, it has essentially 3 phases. There's the bottom-up evaluation of the expression as usual. Then you have top-down propagation of the expected values of the sub-expressions. And finally, you can construct the resulting environment. And we can easily adapt this into an unassume operator with quite minimal modifications. And this will work very similarly. Now we have a more precise state, and we want to relax this up to this kind of inequality. And we can leverage all the same backwards operators to compute possible values for x in this expression. And the important thing here is that here we should not refine this value of x that we find from the expression with a value of x that we currently have in the environment, because otherwise we will never be able to relax anything. Also to note here, we don't have this sub v here because this algorithm essentially chooses the set of variables to relax itself. And this is useful in some cases where a large invariant wants to relax multiple variables in the same expression, in the different sub-expressions of one big invariant, but they might also depend on each other. And we have examples of this in the paper. And to also note that this is not the same as taking the first naive definition and into the assume part of it, just plugging this propagating assume algorithm. And finally, I will just say that this generalizes nicely to the pointer example that we had before and a number of other examples that we provide in the paper. We also evaluate our approach. We do it in terms of precision and in terms of performance. And to do that, we implemented in the Goblin abstract interpretation framework some unassume operators. And for non-relational domains, we implemented the propagating unassume algorithm. And from this experience, we know that this indeed required minimal effort because we could reuse all the backwards operators that were already there. And for relational domains, we implemented the dual narrowing one that we describe in detail in the paper. So first, our precision evaluation, we use a set of examples from abstract interpretation literature, which require some maybe more advanced techniques to infer certain invariants. And the Goblin, it does not implement these techniques. It maybe solves some of them due to orthogonal reasons. But when we manually write witnesses with the right invariants for all of these programs, then Goblin, extended with our witness validation technique, which unassumes these invariants, it can validate all of these witnesses. So it verifies the programs, and it can also prove that the witness invariants themselves are all correct. So we see an improvement in precision on what it can infer and what it can actually confirm. And similarly, we use 2 SVCOM tools, CPA checker and Ultimate Automizer, to produce witnesses for these programs. For witnesses from Automizer, many of them are completely validated. In some cases, we failed to prove all the witness invariants correct, but we can verify the program, which we could not before. So in these yellow cases in this table, we have performed just the witness-guided verification. And this happened more often with witnesses from CPA checker on these programs, at least. And now about the performance evaluation. There we took a set of slightly larger programs, but they're not very big, but these have been used to evaluate Goblin in the past. And first, we just ran Goblin on them as is. We observe some runtimes, and we also have a look at the number of transfer function evaluations that are performed in the fixed point iteration process for these programs. Then we manually wrote the witnesses for these programs with some invariants in them, and we used our technique for witness-guided verification to, again, verify these programs. And what we see is that that the analysis goes both faster and also the number of transfer function evaluations goes down as we expect. So to finally conclude, we made 3 main contributions. We have specified the unassume operator. We have a general instance of it for relational domains that uses dual narrowings. We have an efficient algorithm for the non-relational domains, which generalizes also the pointer variables. And we have implemented these things also in the Goblin abstract interpretation framework. And from our practical evaluation, we see that this indeed, unassuming witness invariants in this manner, can make the analysis both faster and more precise. And thanks for your attention.
Okay, we have time for questions. Patrick?
It's more a comment than a question. It's a very interesting generalization of a trivial thing done in Astray. When you want to check something is an interval, you assume that it is in it and you iterate the fixed point, and then you do one more iteration not assuming, and then if it's still included, it's okay, otherwise it's not. But in Astray, it's only for intervals, so the unassume is kind of trivial. And I think it's very interesting generalization.
So regarding to the unassume operator, all the examples you have shown in the talk are about intervals.
The technique itself is not specific to intervals.
Right.
I mean,
So my
the non-relational things in Goblin as well, we have other non-relational numeric domains. They work for all of them.
So my question was about relational domains. Did you look into that?
In our implementation, we used Apron, so this works both for octagons and polyhedra. And for the precision examples, actually, many of them actually are polyhedral, and we use the.
Okay, so because the question I wanted to get at is that in such domains you have also internal reduction that could reestablish some constraints. So did you have cases where essentially you have to the unassume statement is essentially fighting against the domain which re-adds the constraint that you want to unassume? Like I guess this is, like Patrick just mentioned Astray, and I think we had this in Astray at a long time in the past with bouncing effect. No? Patrick seems confused.
I don't recall if we saw that in any of the examples.
Okay, so maybe we can discuss this offline. David?
Maybe my question is related, I'm not sure, but the assume operator, as far as I understand, sometimes you can iterate it and you gain precision. And do you have a similar effect with the unassume operator?
Yes. So for this propagating algorithm, I mean the assume version of it, you can iterate locally to get things more precise, and actually you can do a very similar thing here. And instead of using you would use widenings also maybe there to get it to do the things. And indeed, if there are sub-expressions which depend on each other, for example, one of the sub-expressions is relaxing a points to set, and the other is relaxing variables through the points to set. They depend on each other. Then you would doing it multiple iterations of this kind of algorithm will actually relax first the points to set and then everything through the points to set.
I have a similar question. I did not understand why it is 3. When you go back, you say up, down, up, or down, up, down, and it's stable, yes. Then why? I'm not sure. Why is it 3 only? That is, why don't you need iterating?
I mean, you can iterate this. I just didn't mention it. It's just one
it's
instance
correct,
of it.
Not optimal.
Okay. Any other question? Okay, if not, we will thank Simmo again, and I will